this video, I will go through a simple example step by step. This example actually will prove automatically, but I think it may be instructive for us to go through each step individually to discuss them in full. You can follow along by selecting File and then Load Project. This gives a full list of projects that are sent out with each version of KeYmaera. And here we'll just choose the ETCS train control, the simple controller. In this file, you can take a look at what the system is doing. We start with some property, some limits on the position of the train, which is z, and its distance to its moving authority, m. Z should never go past m. So initially we have conditions on the position of z relative to m, as well as its velocity, so it can't be going too fast to begin with relative to that distance. And then some constant conditions on the acceleration and braking bounds. We then choose a start braking point to be this complicated formula. If the distance between the train and the movement authority is less than the start braking distance, then we should start braking, and otherwise we're still allowed to accelerate. We then evolve for up to epsilon time with that acceleration, and if we're decelerating and we come to a stop, then we just stay stopped. The property that we're trying to prove, of course, is that the position of the train is always less than or equal to the movement authority. Okay, so the first step that we can apply is this top level operator. You can see which operator is the top level by sort of hovering over the operator, and it'll highlight what its operands are. So here this less than or equal highlights the entire inequality, and the conjunctions highlight the operands that they operate over. So the top level operator here is the implication arrow because it highlights the entire formula. So we click on that, and the rule that we want to prove comes up right at the top, and it's the imply right rule. And this just brings this initial condition that we have over to the left-hand side of the sequent. Now it might also be helpful at this point to apply a few and lefts. This just changes the conjunction into commas on the left-hand side. So these are the things that we get to assume. Okay, now our top-level operator is this star inside of the box modality. So the star is in our hybrid program, and that's a loop invariant. This is covered in a different video. So we'll choose a global loop invariant because those are a little bit simpler to understand. Let me just cancel this for a second. The regular loop invariant is more powerful, but it's also a little bit more complicated. So feel free to play around with that, but for this video we'll just look into the global loop invariant. We're just going to use the loop invariant that KeYmaera finds automatically, and it's just looking at the initial conditions and assuming those as the loop invariant. And for this simple example, that turns out to be strong enough. Whenever we apply a loop invariant, an induction rule essentially, we have three properties left to prove. The first branch is to prove that the property is the loop invariant holds initially. This is like a base case. And if you look at this, we used the initial conditions as our loop invariant, so this should just prove automatically, no problem. The second condition is that the loop invariant we chose actually proves the property that we want to prove in the end. And again, well, we can do the imply right rule if we want to do it completely by hand, but just by inspection we can see that v is positive and v squared is going to be positive. So in order for this inequality to hold true, z must be less than m. So this can just be closed by algebra essentially, but we use the quantifier elimination algorithm. Okay, so now we get into the tougher section So here, essentially, we have the same formula that we had initially, only instead of having a star here, we just have a single execution of our hybrid program. Additionally, instead of proving the simple z less than or equal to m property, we're proving our full loop invariant. So we have the loop, we get to assume the loop invariant initially, and then after one execution of the hybrid program, we have to prove that that loop invariant still holds. So let's do this by hand. Nothing much going on here. So we click on the box modality, and you can see that the top level operator here is a sequential composition. So by doing the sequential composition rule, we just split this into two boxes. And now we can treat this as just a box with an assignment inside of it. And so we get the assignment rule, which just brings this into our state. And then again, we have the composition rule so that we just have a single box with a single operator in it. And now we have the if then else rule that will apply. So if our inequality that the distance between the train and the movement authority is less than or equal to this long formula, which is actually what we call a start braking formula. So if we're getting closer than the distance where we need to start braking, then we should start braking. Otherwise, we're still free to accelerate. So when we apply this rule, the if then else right rule, you can see over here in our proof tree that the if rule actually splits us into two branches. The first branch where the property was true, where the condition was true, and the second branch where the condition was false. In the branch where the condition is true, you can see that the acceleration is going to be set to be a minus b. And in the branch where the condition was false, you can see that we can accelerate still. So let's prove the first branch where we're braking. So now we just have an assignment as our top level operator. And we do all of these things. Usually we don't do these things by hand. These are generally applied automatically by the theorem prover. Okay, so now our top level operator is this differential equation. Inside of the hybrid program, it's this differential equation system. We have a couple of rules here that could be applied because the property that we're trying to prove has a bunch of conjunctions in it. So we could do a box split on that conjunction, which just splits that property up into smaller properties and essentially copies the hybrid program ahead of it. I do not want to do this because then we end up doing an and right and we get two more branches where we're essentially having to do the same proof rules on both of those branches. So I don't want to branch just yet. I'd like to apply some proof rules before having to branch. So we can come back to this split where I sort of changed things around and prune the proof back to where we were. So now we can just look at this differential equation here. And this is a pretty simple differential equation, so we can just solve that directly. So at this point, things start to get a little interesting because we actually have a solution to our differential equation, and that solution has been plugged into the remainder of our formula. So now we have this t0, which is the amount of time that the system evolves. So we're saying that for all time greater than or equal to 0, so the system can evolve for any period of time. And so we have to prove that our property holds no matter what that period of time is. However, the system can't just evolve arbitrarily in that period of time. It has to always satisfy the evolution domain. So if we just take a peek back at the differential equation, how it was written initially, you can see that our evolution domain was that t has to be within epsilon, so it can't evolve longer than epsilon, and that once the system reaches velocity 0, so once the train brakes to a stop, it has to remain stopped. It can't start moving backward. Okay, so for any time greater than 0, assuming that our evolution domain holds for all time in between 0 and t0. So that's this ts value. If our evolution domain held, so the solution of the velocity is greater than, so the velocity at ts is greater than or equal to 0, and ts is less than or equal to epsilon. So as long as we're in our evolution domain for all of the time between our start time and the time when we're ending the evolution, which is t0, then we have to prove that the loop invariant still holds. Now this looks a little bit different than our loop invariant because it's actually the loop invariant with the solution of the differential equation at time t0. So here, for example, we used to have v squared. Now we have the v at time t0 squared, so v plus acceleration times time squared. And similarly here we used to have m minus z. Now we have the position of the train at time t0. Okay, so what can we do? Well, first of all, we have a Forall on the right side of the sequent, so we can do a Forall right rule. And this just replaces t0 with an arbitrary free variable, which we choose as t1. KeYmaera automatically sets that as a free variable. Okay, and then we do our imply right rule. We can do another imply right rule. And now we have a Forall on the left-hand side of the sequent. And remember, this is essentially the evolution domain. So this is saying you get to assume that your evolution domain was satisfied for the entire time of the evolution. So for all ts, for all time between 0 and the end of your evolution, t1, your evolution domain held. Okay? So what we can do here is we can do a Forall Left, which just instantiates this time with a specific variable. So this is only applicable in some problems where you only need to assume that your evolution domain held at the end of your evolution. So this problem is one instance of those. So we can either do a Forall Left and then type in t1, so that works just fine, or we can actually just drag and drop that variable onto the Forall and choose the Forall Left rule. Okay, so now we're making some serious progress. Everything that's left is really just algebra at this point, so we can do a few more things. Here is an imply left rule, which means that we have to prove two different branches. First, we show that the left side of the implication is true in one case, which is easy. So that closes. And then we get to assume the right side of the implication, which is here. Okay, so now this is just algebra, and we can eliminate universal quantifiers. So this is just an algorithm that deals with the first order arithmetic that we have left. We probably could have applied this pretty soon after we solved the differential equation, and it would have worked, but we just went through some rules to simplify the problem that we're sending out to the quantifier elimination. So eliminate universal quantifiers, and you can specify some variables to try to optimize that, but this should just work automatically, so we don't need to do that. The other branch of the if actually works similarly, so I won't go through that here. And since this is a simple problem, we can actually just apply rules automatically, and the whole property will prove. So thank you for listening to this extremely long and somewhat rough tutorial video. I hope it was helpful.